Good afternoon, everybody. I'm Patrick, and it's my pleasure to chair the last talk and the last session of this conference. And we are going to hear by Pau about quantum information experiment with single atoms coupled to cross cavities.
Yes. Yeah, thank you. It's a pleasure for me to give the last talk of this nice conference. My name is Pau Farrera. I work in the Quantum Dynamics Division of Professor Gerhard Rempe at the Max Planck Institute of Quantum Optics. And I'm also MCQST START Fellow. And today I will be talking about some quantum information experiments that we perform using single atoms coupled to cross fiber cavities. Okay. Not working? Should be on. Not really.
Just use the arrows.
Okay, yeah, I will use the arrows. Yep. Okay, yep. Okay, so the experiments that we perform can be seen as an evolution of the single atom maser which was developed in Munich in the group of Professor Herbert Walther. If you can look at this image, you can see that they had an atomic beam where the atoms then were going through a velocity selector and then interacting with a microwave cavity, with intracavity field of a microwave cavity, and then going to a field ionization and then detected by a channeltron. The experiments that we perform are a bit different, so we are using optical cavities, and we are using atoms which are trapped and laser cooled at the point of maximal coupling to the cavities. And instead of using an intracavity microwave field, we are using flying single photons which interact with the atom. And our motivation is to then to explore schemes in quantum information which combine qubits encoded in atoms with qubits encoded in single photons.
You can use the laser pointer.
Okay, yeah. Okay, so the motivation is actually that encoding quantum states in single atoms is good for the storage, processing, and synchronization of this quantum information, while encoding quantum states in single photons is good for the long distance distribution of this quantum information. So by working with an interface of photonic and atomic qubits, we aim to combine the advantages of these two types of qubits. And we look for applications in the field of quantum computing and quantum communication or cryptography. And we can maybe have a long-term vision, maybe in the long-term future, where distant nodes can exchange quantum states encoded in photons within applications in building quantum communication repeaters, distributed quantum computing, or distributed quantum sensing. So in our group, there have been many experiments performed in the last years with this platform, with single atom coupled to optical cavities. There have been photonic quantum memories implemented, also quantum computing gates between photonic qubits and atomic qubits, also remote gates between two atomic qubits mediated by a photon, and also very recently the generation of multi-photon entanglement of entangled states of up to 14 photons emitted by this atom cavity system. The way these setups look like, the central part can be seen in this image. So you can see here at the center of the image in orange, the two mirrors. So these are based on bulk mirrors with around 1 centimeter of size and around 500 micrometers of intracavity distance. The cavities that we use, however, are a bit different. They are based on fibers. So these are fibers where the tip has been cleaved, and then using a powerful CO2 laser shine onto the tip of the fiber, then high spherical, so some material of the surface is evaporated, and this generates a high quality spherical surface on the tip of the fiber. And later these fibers are sent to a company to introduce a high reflective coating at the tip of the fiber, which then forms the cavity mirrors. So indeed, by combining two of these fiber tips, we can build cavities. And having these fiber cavities for us has several advantages. So first of all, because with these fiber tips, we can put them closer together, and with the CO2 machining technique, we can achieve a smaller radius of curvature. Then we can achieve smaller mode volumes for the cavity mode, and therefore achieve a stronger interaction between the intracavity field and the atom. The second advantage for us is that the emission happens directly into the fiber, and therefore it's easy to us to then distribute these photons into a different location in the lab. And the most important advantage for us is that because fibers have a small transverse extension, then we can have two cavities with small mode volumes, and therefore coupled to a single atom in the high cooperativity regime. Okay, so here you can see an image of how the setup looks like. This is the inside of our vacuum chamber. If we zoom at the center, we can see these four fiber tips, so forming the two optical cavities with intracavity separation of around 100 micrometers. And we trap single atoms at the center. And our motivation is to then use this system to explore schemes in which two different transitions of our atoms, which are rubidium atoms, are coupled to each of the two cavities, and to use these schemes for tasks in quantum information. So that's what I will be talking about today. So I will initially tell a few more details about the experimental setup, and then I will talk about three different schemes that we implemented, one being a heralded photonic quantum memory for polarization qubits, then a nondestructive detector for photonic qubits, and finally a scheme in which we generate photon pairs emitted in these two cavities. So a few more details about the experimental setup. Here you can see again a picture of the inside of the vacuum chamber. We have rubidium dispensers. We have a vibration isolation system to mitigate vibrations of the optical table being transferred to the cavities. We have big groove holders which hold the fibers in position. We have microwave antennas which allow us to drive the ground state transition in rubidium. We have 11 piezo actuators, so 7 slipstick stages with a long tuning range which allow us to bring the fibers into the exact position to form the two optical cavities. And we have 4 shear piezos which allow us to actively stabilize the length of the cavities. And we have 2 mirrors inside the vacuum chamber which allow us to direct 3 counter-propagating laser beams which allow us to form magnetic optical traps, so a cloud of laser-cooled atoms 1 centimeter above the cavities. So after creating this cloud of atoms, what we do is we release the atoms, we let them fall into the intracavity region, which you can see here, where we have the 2 optical cavities with finesse around 15,000. And then using 1 vertical red detune trap and 2 blue detune intracavity traps, we then trap individual atoms at the cross point of the 2 cavities. And we have an imaging system consisting on a custom aspheric lens, which allows us to collect light emitted by this single atom with a numerical aperture of 0.3, and to then observe these trapped single atoms. Okay, so now I will move to the first scheme I want to talk about today. This is heralded photonic quantum memory for polarization qubits. So here the idea is that we come with polarization qubits in one of the cavity, and the polarization state of the photonic qubit is then mapped into a spin state of the atom. And during this process, there is actually a photon being emitted in the second cavity, telling if the storage of the photonic qubit succeeded or not. So in a bit more details, the way this works is we have a magnetic field pointing in the direction of the qubit cavity, and then in the frame of the atom, the polarization state of the qubit is a superposition of sigma plus and sigma minus polarizations. And for the qubit cavity, the cavity is degenerate for the two polarization eigenmodes, so such that they are both supported by the cavity. While for the other cavity, for the blue cavity, the Herald cavity, there is a birefringence such that the two polarization eigenmodes of the cavity are shifted, and only one is resonant to the transition, to the blue transition, the Herald cavity transition. And therefore, the polarization qubit is mapped into two defined spin states in the rubidium atom with MF-1 and MF+1. And then after studying the state in this spin superposition, we can actually map it back into another photonic polarization qubit by just shining pi polarized light along the shore cavity, the blue cavity, the one which was used to collect the Herald photon. So in order to be highly efficient for this quantum memory process, we actually need to operate in the impedance match regime. So this means that the light reflected in the first mirror of the qubit cavity interferes destructively with the light which enters the cavity and then is transmitted via the same mirror. And for this to happen, we actually need a high cooperativity in the two cavities. So the efficiency in this scheme is 11% for the Herald generation and detection. This includes generation, transmission, and detection losses. And later for the readout efficiency, we have 56%. And we can preserve the qubit with a fidelity of 86% in the case that we don't consider only the Herald cases, but if we consider only the cases where a Herald photon was detected, then this mitigates error and the fidelity goes up to then 95%. And we can, in this experiment, we could store the photonic polarization qubits for a few tens of microseconds, which limited by the coherence of the spin superposition. Okay, so that was the first experiment I want to talk about. The second experiment I want to talk about is a nondestructive detector for photonic qubits. And here the idea is that photonic polarization qubits are reflected in one of the cavities while impinging a change on a state of the atom. So the way this happens a bit more and then this change in the state of the atom, we can detect it via the second cavity. So the way this interaction with the photonic qubit and the atom happens is the following. So for this, we need an atom with two ground states and one excited state. And we need a cavity which is single-sided. So this means that the transmission of one of the mirrors is much higher than the transmission of the other mirror. In this situation, when a photon enters the cavity, it bounces back and forth. When the atom is in the ground state not coupled to the cavity, a photon entering the cavity, it bounces back and forth, and it exits the cavity via the same mirror with a pi phase shift. However, when the atom is in the ground state, which is coupled to the cavity, then there is a normal mode splitting of the atom-photon energies in such a way that the photon cannot enter the cavity but is reflected in the first mirror, therefore with no pi phase shift. So that's how the detector works. The idea is to put initially the atom in a superposition between the two ground states, then to reflect photonic polarization qubits from this qubit cavity in such a way that the component with the atom in state 1 acquires 1 pi phase shift. And then after this reflection, if the state of the photonic polarization qubit and the state of the atom remain separable, then this pi phase shift happens on the state of the atom. So that's how we operate the detector. We initially put the atom in a superposition between the two ground states by using microwave signal. We then reflect photonic polarization qubits, which then induce this pi phase shift on the state of the atom. Then we perform a second pi/2 rotation in such a way that the state with a pi phase shift rotates into state 0, and the state with no pi phase shift rotates into state 1. And then we perform cavity-enhanced fluorescence atomic state detection to see if the atom is in state 0 or state 1, telling us if the photonic qubit was reflected or not. So for us, having two cavities is important because then we can have one cavity in a transition which is suitable for the interaction between the polarization qubit and the atom, and the other cavity is in a cycling transition in rubidium, which is suitable for the last step for the cavity-enhanced fluorescence atomic state detection. Okay, so here we can see the histogram of the events. We can see the first microwave pi/2 pulse happening in 7 microseconds. The reflection of the polarization qubits, we actually use weak coherent states. Then the third step, the second microwave pi/2 rotation. And then finally, we can see that in the situation that no input photonic qubits are reflected, there is a high level of the fluorescence counts, meaning that the atom is in state 1. And when input photonic qubits are reflected, we see a low level of the fluorescence counts, meaning that the atom is in state 0. So we can do this with an efficiency condition on a reflection of the photonic qubit and on destructive efficiency of 80%. The detector works with dark counts of 3%, and the fidelity of the output qubits with respect to the input qubits is about 96%. So we envision few situations in which such a detector could be useful in quantum communication. So these are situations in which such a non-destructive detector could tell the sender and the receiver if a photonic qubit was lost along the communication line. And this could be useful in several situations. It could be useful, for instance, to spare time and expensive resources. And here one example is, for instance, if you have long distance entanglement between the two atoms that you want to use to teleport a photonic qubit. So you only want to use this entanglement once your photonic qubit is there, and this you can ensure it by using such a non-destructive detector. It can also be useful to perform qubit measurements which are sensitive to loss. And here one simple example is if you have a qubit measurement which is noisy, then by having such a non-destructive detector, you could choose only to open the gate of the qubit measurement when the photonic qubit is there, and therefore reducing noise. And finally, such a non-destructive detector is also one ingredient for QKD attack. For the photon number splitting attack, you need such a non-destructive qubit detector. Okay, so now I move to the last experiment I want to talk about, and this is the generation of photon pairs generated by in these two cavities. So here, one of the motivations is that rubidium has a telecom transition coupling one excited state 5p3 and another excited state 5d 5 half. And the experiment that we would like to implement in the future would be the following: would be starting with the atom in MF equal 0 in one of the ground states, to then excite it to 5d 5 half, 4d 5 half, and then in such a way that the atom emits a superposition of sigma plus and sigma minus photon, and then mediated by the second cavity with a pi mode of the second cavity, which brings the atom in a superposition of states 0 and 1, entangled with the polarization state of the telecom photon. So we actually have a proposal on how to use this scheme to build an efficient quantum repeater. However, the cavities that we have are coated for light at 780. They don't have a good coating for telecom, and at the moment we didn't want to change the cavities. So therefore we decided to first explore this scheme by using photons, by using the 5p3 half to 5d 5 half transition, in this case at 776 nanometers, for which the cavities are well coated. So that's what we do. We start by initializing the atom in one ground state. We then excite the atom to the state 5D 5-half, and then we wait for emission of photons in the cavities resonant to states 5D 5-half and 5P 3-half transition, and the 5P 3-half 5S 1-half transition. So when we look at the photons, we can see that we can emit photons with efficiencies of around 20%. And if we look at the efficiency of having one photon when we detect a photon in the other cavity, this goes up to 45%. The duration of the photons is given by the Purcell enhanced emission by our rubidium atom into the cavities, which compared to the free space decay of 230 nanoseconds give a Purcell factor of 1.8. And we also measure the G2, the autocorrelation function of these photonic fields, and we measure values of around 0.1, showing single photon statistics of the fields. We also measure the cross correlation, so we look at the correlation between the two photons, and we see a correlation peak of around 10 nanoseconds, telling us that the photons are temporally correlated. And this is actually detrimental when you want to interfere two photons of two independent sources for a homomandal interference experiment. So in this case, using simulating the atom cavity Hamiltonian, we calculated the visibility expected in a homomandal interference experiment, and we obtained 0.12 for the case of our source. However, having two independent cavities allows in principle to change the properties of one cavity with respect to the other, and we could go into the stronger coupling regime for the upper cavity, and in this case then the visibility would go up to above 95% in a situation where the correlation peak width is comparable to the width of the photons. So I mentioned that anyway we would like to have the photons at telecom wavelength. Just to illustrate how important this is for us, let's imagine that we want to distribute photons between Garching and Munich. If we distribute the photons at 780, actually the probability for a photon to go from Garching, to travel from Garching to Munich is around 6 × 10⁻⁸. However, if we could change the frequency of the photons to 1550 in the telecom band, even if we lost an efficiency of 50%, then the transmission probability would go up to 20%. So because of this, we decided to explore the frequency conversion of the photons and to build quantum frequency converters based on difference frequency generation. So in this case, we overlap single photons at 780 with a pump at 1610 nanometers, and through difference frequency generation, there are photons generated at 1513 nanometers. So we build such a converter device. We overlap light at 780, so the photons at 780 with a pump in a nonlinear periodically poled lithium niobate crystal waveguide. And we do this in a Sagnac configuration. We split the two polarizations, and they are both converted in the same crystal in such a way that we achieve passive phase stability, and therefore the polarization of the qubits can be preserved. So we choose this pump wavelength at 1610 nanometers because then the photons lie in a region with low noise far away from the Raman noise coming from Raman scattering in the waveguide from the pump. And we can observe that we can convert the photons with an efficiency of around 50% for the two polarizations. So after assembling the converter, we decided to try to convert single photons emitted by our rubidium atoms to the telecom band. And we can do this with a signal to noise ratio of around 70 and preserving the single photon statistics with a G2 of 0.05. So with this, I come to the conclusions. I show that we have an experimental setup where we trap single atoms at the center of two crossed fiber cavities. I mentioned that we implemented heralded photonic quantum memory for polarization qubits. We also implemented a non-destructive detector for polarization qubits, and we generated photon pairs mediated by the two cavities. So with this I finish. I would just like to thank the team that participated in all these experiments, and thank you for your attention.
Thank you very much for your talk. Do we have questions? Okay, if there are no questions, then I have one.
Sure.
You showed in the first experiment the kind of heralded photonic memory. You showed kind of a lifetime of that memory, which was around 90 microseconds, I think. Is there kind of a direct source that you could kind of tune to make that longer? Because I guess that would be interesting.
Yeah, indeed. Actually, now we increased the coherence time to around 200 microseconds. So, yeah, at that time we had really magnetic field noise coming from devices close to the atom, and also problems with differential light shifts. So coming from the trap, yes. But yeah, now we could improve on those things, and now we are at a few hundreds of microseconds. Yeah.
Thank you very much. There's a question about that over there. There's a red cube over there. Oh, okay, or like that.
Can you explain again why you have to lift the degeneracy for the heralding cavity for the two polarizations?
Yeah, indeed. So, okay, maybe I come back to the slide to see it clear. Here. Yeah, exactly. So if the herald cavity was not birefringent, then there would be different transitions allowed, and therefore the two polarizations would not end up in a single spin state. So in the end, we want to have a superposition of two spin states in rubidium, and this is only possible if there is only one decay path for the photon. If the two polarization modes were degenerate, then it could also decay in this state or in this state here. So then there would not be a one-to-one map between the two polarizations and the spin states. Yep.
Okay, but how do you make sure then that both decays, so both blue decays in your figure, can happen simultaneously? Are they not at the same frequency?
Yeah, they are at the same frequency, and they happen simultaneously. Yeah. But what is important is that only these pi decays happen, but not decays into sigma plus and sigma minus. That's the important part.
Okay.
Yep.
Thanks.
Sure.
Are there further questions? If not, then let's thank Pau again for his talk.